Okay, this is the continuation of the last video. We are setting up a seismic analysis for an embankment dam in FLAC using the Moore-Coulomb soil model, and we're going to include pore pressure, excess pore pressure generation during the dynamic portion of the run. So, where we left off last time was here, assigning the material, the soil, Moore-Coulomb soil material, or soil model to all of the regions in the FLAC model. So you can see that we were looking at the friction last time here, and so it's been properly assigned. And I wanted to note that the permeability is in units, not feet per second or centimeters per second, and you have to look it up in the FLAC manual to see how exactly what they are, or I might have them here. I don't. I have them listed as feet per second, but this is not what FLAC accepts. It needs a permeability in specific units, and it's easy to convert, but you'll just have to look that up. Okay, so like for example, this number is a weird unit in FLAC. Okay, so the next step here is to get ready to go. We're trying to go for the solve elastic, and remember, you can follow along and just type in everything you see here into your own text file and then call it into your own demo version, and you can replicate this entire process. So we're paused here, and what we're going to go from this pause to this pause here on line 112. And what we're doing is we're assigning some saturation to the embankment. No reservoir has been created yet, nothing like that. So we're just going to do continue, and this assigns 0.9 everywhere, and then it assigns 100, so this is 90%, and this line 111 assigns 100% saturation only to the bedrock and foundation grid points. So let's see if what happened. So obviously the friction is not going to change, so we are going to plot model. We want to see a model of the saturation. It's in groundwater here, and if we want the grid on the outside, go like that. Okay, call it saturation, and now we can zoom in, and we can see it's contour plot 0.9 for the embankment and 100% for the foundation. So this is assuming there's a pre-existing groundwater table that we're now modeling that probably runs right here horizontally from toe to toe. This is like simulating something right after construction. So you can tell we skipped, we didn't do a staged construction in this, but that's not what this is for. You can do that if you want later, or in a different analysis, I mean. So the next thing is to actually put a groundwater table in. I mean, we have made the saturation as so, but now we're going to put in some pore pressures. And the way we do that, we're going to put in some hydrostatic pore pressures. We're going to create a table 39 with ID 39, and then it's going to have 2 points. On the far left here, we're going to hit this XY. Now we have XY coordinates down here in the bottom left. So around here, you can see this is negative 6980, about this corner, and this line goes from that point all the way to this point, 79.980. So after you create a table, now you can use the command water table followed by table 39, which will activate any pore pressure, static pore pressure below that line. So this is one way you could make a phreatic surface. In this case, we are just making it a water table, horizontal water table. So I'm going to do continue, and we're going from line 112 to line 116. And we can see here, if we plot pore pressure, GPP is grid point pore pressure, pore water pressure, and we'll put grid on top of it. So you can see that it says 0 because no pore pressure has been applied, only the saturation. So after this should become filled up with pore pressure. There we go. So anything above the toe of the dam in the embankment is 0, this color, and then anything below this line is some kind of pore pressure. So just based on hydrostatic pore pressures. Okay. So then the next thing we're going to do as you can tell here that there are no boundaries here, so we're going to fix some boundaries, and we're going to fix them, and this fixes the bottom in the X and Y direction. We're going to fix the upstream end and the downstream end in the X direction. And so if I do continue, we're going from line 116 to 122. And now you can see that these boundary conditions showed up. So B is like both directions, X and Y, and X only is here. So the other side should be X only too, and it is. Okay. So we will go ahead and continue. So the next step is to solve elastic. So the first solve, it doesn't have to be, but it usually is the solve elastic. So there's no reservoir yet, there's no phreatic, there's only a groundwater table. And so the solve elastic will give us our initial static stress state. So the shear modulus was input above here for each soil model here, shear modulus, and we did not do it based on depth. So, some users like to use the shear modulus based on depth using the K2 max equation, and they can do that. If you do it that way, it's an iterative procedure. If you do it this way, it's a little bit more simple, and you just put a shear modulus in, and maybe you base this number off of some kind of shear wave velocity, for each group. So there's going to be a different shear modulus for each soil group. And maybe the shear wave velocity takes stress into account. So we're going to do solve elastic. Solve elastic does two separate solves, one when it's more coolant, one when it's elastic. And we'll get an initial stress state. So we will say continue. And now we'll notice, so that thing that popped up ran through some steps. And we are going to now plot the effective stress. So that's in contour. Effective stress is ESYY is the vertical effective stress. And we're going to just say vertical effective stress. Okay, and we're going to give it the grid on top, and we're going to say okay. Okay, so this looks pretty much like you would think. Now notice the sign convention is backwards in FLAC from geotechnical engineering. So let's see, the compressive stress is negative, when in geotech it's actually positive. But here's the, legend. Okay, so the solve elastic worked. So what someone could do here is, you could find a lateral coefficient, or earth pressure coefficient, and plot that up, and that would probably be a reasonable thing to do. I'm not going to do that in this case, but at this point you could do that. This isn't the final initial static stress. We have to add the phreatic surface, the reservoir pressure, and some other things. So it might be more prudent to look at the earth pressure coefficient at that point. But for now, it's good enough to look at the effective stresses, and it looks pretty normal, higher underneath the crest, as expected. Okay, so we just did the solve elastic, and now we're going to set up some history points. Okay, so these are the history points that we're going to be looking at. I have the crest up here. We're going to follow the displacement of the crest, but also we're going to look at some items, some parameters for these two elements down in the downstream foundation. So you set a history by doing history, and then every history point has to have a identification number. And PP stands for pore pressure. This is shear strain, engineering shear strain. Well, if you times it by 2, it's engineering shear strain. Here's a shear stress, and here's a volumetric strain. So I'm doing that for a couple. I'm also doing upstream foundation. I didn't show that on the figure, but these two, the 23.3 and the 33, are the two that we looked at. Importantly, I'm giving history number 50, so I skipped from 14 to 50, but I'm giving that the dynamic time. So now we can plot, for example, shear stress versus time. If you don't have time on here, you just have shear stress versus step. Okay, and also this hist end step on line 157 tells FLAC how often to sample the history. So this is every 150 steps. Speaking of steps, we did do a solve elastic. And during that time, you saw that window, the solve window, briefly flash. And we have now, you can now see where we are. We're on step 572. So when you're in the model tab, there is no record of the step number you were on. But if you're on any plot that you created, you'll see 572 keeps showing up. That's a quick way to get step. You can also write a fish function to find what the step is. But because it's a variable that FLAC keeps track of. But we don't need that for now. So just importantly, I always, identify or tell FLAC to monitor the dynamic time and have an end step of some number. The default of end step is 10. 150 seems to work out pretty good. Okay. So the next thing we're going to do, so right now we're paused here. As you can see, paused, solve elastic. Oh, just kidding. We're paused here. Okay. So that's why it's good to look at. So we're going to continue. We're going to go from line 127 to line 158. Okay, so continue. And now we have assigned all the histories. So you can assign the histories at any time. I'm doing them here. You could assign them right before loading starts, but we still have a ways to go because we have some other static solves that we're going to add to this after we do the certain things such as add a phreatic surface and such as adding a reservoir. So the next thing we're going to do in step 6 here is add the reservoir pressure. And here's like a little schematic of what we're thinking of doing here. So we're going to write a command that says apply pressure from this grid point 1.5 up to 1210, and the amount of pressure that you need to apply is equal to 10.5 feet because that's what the distance is, and the pressure is about 655.2. So that's what we've done here. Apply pressure. Here's our 655 number, and it varies from 0 to 655, and then from this grid point to that grid point. So you can read up more in the FLAC guide or in my FLAC guide that I've made or the FLAC manual about how this command works. But essentially that's what it's doing. And now we're going to do a solve right after that because the stress state should change a little bit or maybe a lot. Let's see. Do continue. Okay, so now we've stepped up to 1357 from 572. And you can see that the stress state did in fact change. The reservoir pressure is being felt along the edge here. It's no longer 0 everywhere, right? You're seeing some of the pressure from the reservoirs. Okay, that's interesting because this is effective as well. Yeah, that looks right. Okay. So the next step, so we just applied the reservoir pressure. Okay, so the next step is to apply the boundary conditions in preparation for a seepage analysis, right? So the boundary conditions that we need for the seepage analysis are shown here conceptually. This is a standard thing, right? Total head boundary condition under the reservoir here. What GeoStudio and SeepW calls a review node. So something that might get wet because the phreatic surface could pop up down here. We don't know. That's right along this area, this boundary. And then we have another total head boundary over here on the downstream end where we can dictate where it should exit the downstream end. And then this green highlighted is an impervious boundary condition. So someone could make that some other boundary condition, but I made it pervious. And in order to make it impervious, there's no action or command that's needed. That's just the default. If you want to have a review node, you have to use this fix PP and then you put IJ next to it. So one at a time. And you have to free the saturation one grid point at a time with an IJ. To do a total head boundary, you can use this apply PP command, pore pressure command, which is different than the apply pressure command that we just used for the reservoir. And you can do this one, looks similar to the apply pressure command. You do it for an entire area. It's not by grid point. Okay, so let's see what that looks like with the FLAC commands. So here we're going to apply the pore pressure. This is the total head, and this is kind of the same setup as that apply pressure command. You can see they look similar, although they are different. And this is applying it on the upstream face. So let's go ahead and do continue and apply that. And let's go to the model tab. You can see that something has changed here. So there's a little P and there's these little blue triangles. Maybe you can see them, maybe you can't. That says that there's a pore pressure command has been applied. Now we're going to do the downstreams end. This is the total head boundary as well. And I'm going to do continue. Okay, so now we're here. We just executed that. So if we hit refresh, now the total head boundary shows up over here. Now we're going to do the review node. So remember, these are grid point by grid point. All right, and so you could probably write a fish function to make this easier, but for now, you know, maybe it's easier just to put these commands in. So I'm doing it for every grid point gets two commands, a fixed pore pressure and a free sat. So you can tell that the IJ here is the same as the IJ here. All right, and so the IJ here is the same as the IJ here. All right, the difference is what's happening. You're fixing the pore pressure, or you're freeing the saturation. Okay, so we're going to run that code from line 183 down to line 225. Remember, we were building the boundary conditions for a seepage analysis. Okay, refresh, and now you can see that these boundary conditions have been set, the review nodes. All right, so what we are going to do next, okay, so for the actual seepage analysis, here we go. The water bulk up to this point at line 227 has been set to 0. But when you run a seepage analysis, you need a value for the water bulk modulus, right? So this is not the actual value. The actual value should be around 4.2-ish PSFs. This is not that. This is much lower. And it's okay to do this when you do a seepage analysis, to have a low water bulk modulus if you are concerned with a steady state seepage analysis. If you want to do a transient analysis, you should give it the real value here, right? But this is kind of a little trick to make it run faster. And so the other things we need to do for the seepage analysis is we need to set flow on, so then flow can go between the elements, and we need to set the mechanical feature off, because this is not, you know, when you run a seepage analysis, it has nothing to do with the mechanics. You know, it's just like when you did a flow net. If you do a flow net on paper, you don't need to know the effective stress. That's why mechanical's off. And we're going to set this fast WB, fast water bulk, on. This also helps with the speed of the solve. Now this is a very fast solve, but sometimes these seepage analyses can take half an hour or more to solve. This is such a small model, it doesn't really matter. And so when we hit the solve here, that's a seepage solve. Okay, so let's go ahead and do that. So we're going to go from this pause to this pause. We're going to do continue. And well, let's look at the pore pressure before. Right now, the only pore pressures are those hydrostatic pore pressures at the groundwater table. And we hit continue. And now it's running through. It's a seepage solve. Now it's done. And now look at the pore pressure has changed, right? Now it looks like the phreatic surface, right? Anything above this is 0. So that's what has happened, and that is a seepage analysis solved. And now we are going to, and this will be the end of, we'll stop here at this line 223. So to get from 232 to 243, we need to set we have to undo everything from the seepage analysis and go back into a static solve situation. So flow was set on here. We're going to set the flow off here, right? Because during a static solve, static drain solve, we don't want the pore pressure going, but we don't want migration between elements. And mechanical off for the seepage analysis. Now we have to set it back to on for a static solve. And we're going to turn this fast WB, which was on for the seepage analysis, we're going to turn it off. Okay? And we're also, importantly, going to make the water bulk modulus set it back to 0. So this is going to be like a drained solve. This is steady state seepage, so this is a drained static solve. And this solve right here is a drained static solve. And we're going to hit continue. And it solved it. So now we're up to step 23,681 because it includes the seepage solves. Let's look at the vertical stress. Okay. Didn't change that much. Let's make sure this is the effective stress. Yes. Okay. So now, well, it did change here. Right? This is 0 now. So it looks good. Everything looks good. And we're pausing here. So the next, hopefully in the next video, we will get through the rest of it. So we're getting closer to the dynamic loading portion.